Okay, everybody. Exam 2 review land. Let's get started. I didn't check this morning as to what the status was of homework 6.2, but I know that homework 6.2 is a long homework. So if I was a betting man, I would imagine my TA is still working on that. Homework 6.3 and 6.4 were simultaneously due today, but 6.3 was just the screen capture homework. What I'll do for homework 6.4 is I'll probably post that sometime tonight or tomorrow. My afternoon will be a little wonky today because my daughter has a half day, so I got to go pick her up and whatnot. But I'll get that posted as quickly as I can. But today, the star of the show is the exam review. So I'm going to talk a little bit about the exam, and then I'm going to open it up for questions. And those questions can be a number of things. It can be, do you want me to go through some homework solutions? Do you want to maybe try and look at like a problem or two to see, anything to clarify? Because again, I want you to do well on the exam. I want to emphasize, though, a couple things about the exam. Well, first off, did everybody get the code? Okay. So the first thing I think I want to emphasize about the exam, and I mean this when I say this, is my rule of three, okay? I feel like on this exam, I've really got to convince you that the rule of three still applies, because I feel like homework 6.2, you're like, come on. Like, what are we talking about? There's no way that a rule of three is going to apply. Trust me, it does. Trust me, it does. And I'll give you an actual hyper-specific example on the exam to just make a point. And I'm not telling you what's on the exam, but you'll get the idea. So, spoiler alert. You're going to have to draw shear moment diagrams on the exam.
Seriously?
Yeah.
I'm not taking this test.
Bruh, I know. But, so, I love my job. So one of the things that I did on those problems, or problem, I'm going to keep that part to myself, but I literally put the space with the line for the shear, the line for the bending moment. I've got the vertical lines drawn. It all lines up. So that's one thing you don't have to do, okay? If you remember on the first exam with the deflection for the truss, like I gave you the table at the bottom. It had all the Young's moduli for all the members, all the cross-sectional areas for the members. The lengths for the members were already listed. So all you had to do was list the real forces, the virtual forces, and calculate it. So there's a lot of that like groundwork that has already been done on this exam to me, your ability to draw a table is not a test of your understanding of CE 312, but it does take time, So I've done a lot of groundwork to make that stuff not a problem, okay? So, and I'll also say that, like in crafting this exam, I have an explicit interest in testing you really solely on the stuff in CE 312. And I'll give you an example of what I'm talking about. When I was in grad school, I took a course on mechanical vibrations. It's the math that you need in order to assess earthquakes. And I remember my final exam, instead of the beams being 20 foot long, they were L long, and everything was symbolic. And I remember doing the problem, and I remember, like, at one point I'm doing all this algebra, and I go, this stopped being a vibrations problem about 20 minutes ago, and now it's just alphabet soup. I'm just doing algebra to rearrange this and solve. And I remember leaving that problem thinking it was 70% an algebra problem and 30% a vibrations problem. Does that make sense? And I decided a long time ago that I'm going to try and avoid that when I make exams in classes like this. Now, I'm not saying you're not going to do any algebra. I don't think I can make an exam where that's possible. but I'm trying to make a lot of that as minimized as possible. Are you going to have to, you know, do some algebraic manipulation? Yes. Are you going to have to take an integral here and there? Yes. Am I trying to avoid this being a regurgitation of Math 229 or algebra? Absolutely. Okay, I don't want you to have to do all that again. Okay, does that make sense? So I promise you the rule of three, it does still apply to this exam, I promise. Okay? All right, formula sheet, same story. Exam structure, by the way, same story. One set of conceptual questions, 3 workout problems. Okay, so same story there. As for what's on the exam, I don't think I can get around support reactions being on the exam. If you remember for exam 1, I had what I would say is a focused problem specifically on the computation of support reactions. It was I don't want to say it was tricky, but it was a problem that had all of the essentially a lot of the different load components that we were looking at, and the goal of that problem was to compute reactions. That's not the goal of this exam. In my opinion, you've already been tested on your ability to compute support reactions, but you need to compute support reactions in order to draw shear and moment diagrams and things like that. So you do need to be able to compute support reactions. I can't make that go away, okay? But really the star of the show is shear and moment diagrams. Make sure that you can determine the internal shear and moment at a given point. Make sure that you can formulate expressions or functions for shears and moments for any beams and frames, and make sure that you can graphically construct shear and moment diagrams. And then finally, there's deformations. Make sure that you can analyze real structures and virtual structures, specifically beams and frames. Make sure that you can compute displacements and rotations. And also account for axial and flexural deformations as appropriate. And essentially what that means is that if you're accounting for axial deformations in a frame, they should be pretty tiny compared to the flexural deformations, okay? And then the rest of this is just the sort of greatest hits of stuff that I think would go well on a formula sheet. Things like, you know, we are still going to have to deal with distributed loads and idealizing those into point loads. Incline loads may show up, I'll admit. That's probably going to be pretty rare that you have to deal with that, but they may show up. Incline rollers, pretty rare that that's going to pop up. Cutting sections through members and hinges, that's definitely going to show up. I mean, the necessity of cutting a section and drawing a free body diagram and writing expressions for shears and moments, that's definitely going to be there. We're still using the same graphical or calculus-based relationship between loads and shears and moments, and the same conclusions for our graphical approach regardless of the types of problems that we're addressing. And we do have our virtual work expression for beam deflections. So the deflections are computed as the integral of little m big M over EI. We sum up as many integrals as we need to fully compute the deflections, because we're summing up all of the energy generated by your virtual loads going through real displacements. We have our unit conversion for rotation, unit conversion for deflection, because there's a mixture of units. We have foot kips for the moments, but we have inches for KSI and inches to the fourth for ENI. That's basically it for in terms of what's on the exam review. The floor is yours for Q&A.
I have a question about using a coordinate system. I don't know what to ask about it. I think it just confuses me a little bit.
So
setting it up.
Let me ask it this. Let me turn it around to you this way. Homework 6.2 or homework 6.4, which is the one that really sort of tripped you up?
I would say both.
Okay. You want to pull up the solution for 6.2? Let's pull it up.
I guess I'm asking I feel like in my mind I was do I need to use a coordinate system even though you said it's a good idea?
So let's go through it.
Okay.
Okay. So do you want to look at problem 2 or problem 1? I feel like problem 2 is the one where coordinate systems really became a thing. In problem 1, problem one, what I did is I defined my origin at the free end and my axis essentially going this way. But I mean, I told you all what the coordinate system was for problem one. And the reason I did that is because when you cut a section and look to the left, you don't need to consider the support reactions. Like, you don't need to worry about it, okay? So we cut a section, look to the left. We still have 1x times x over 2 as our moment from the distributed load. That doesn't change here or here. The one thing, however, that does change is that, so if you look at your two moment functions for the real structure, you know, M1 and M2, you have to account for the fact that you have this point load, so it's 30, and then the moment arm from here is x minus 10. So you have this negative 0.5x squared from the distributed load, and then you have this negative 30x minus 10 for the point load. That has to be resisted by m over here. So essentially what's happening is you're drawing this according to its positive sign convention, but regardless of whatever value that you plug in for x, you're going to get a negative answer. And the reason is because if you actually draw the moment diagram for this beam, it's all negative, okay? Does that make sense? I mean, that's what the moment diagram looks like for the real structure, okay? Now, that's the real structure. For the virtual structure, okay, so if we're finding, let's say, deflections, well, there's only a single moment function, and again, it's also all negative, and the moment function's just basically going to be x, or negative x. So for deflections. So for deflections, it's negative x. For rotations, it's negative 1 because the beam's subjected to constant bending moment. So in problem one, the issue of the coordinate system is probably pretty easy to deal with because it was given to you. So you just chug out your integrations and plug it out. Like I said, the deflection and rotation on this one's going to be pretty big. But I don't think that fully addresses your question. I think your big question is about problem two. Okay, so let's look at problem two. This structure is a little complicated. There's an internal hinge, there's a fixed support here, there's a roller here. So I think just right off the bat I decided let's go ahead and draw a coordinate system this way and a coordinate system this way. Whether we use it or not doesn't really matter, but let's just go ahead and have them there, okay? All right. Now, like I said in class, I think that the first thing that you should do is draw the shear diagram, draw the moment diagram. And for this problem, I think it meant more than any of the others. So what I did is I computed the support reactions, and I got this, okay? So before we go down the rabbit hole on here, one thing I will say, this is one of the things I was kind of talking about in the exam review a second ago. Like, you do have to be able to compute the support reactions to do these problems. So if you didn't get 12 kips here, 29 kips here, and 464 foot kips, like, that's something you ought to review. Just period, you know, because that's going to show up no matter what. Now, here's what my shear diagram looked like. Here's what my moment diagram looked like, okay? So my shear diagram, I go up, over, then I have point load down, and then this is my distributed load, okay? So what that means is that my moment diagram is a line here, and a parabola there. Okay, does everybody see that? So line, line, parabola, okay? All right, so let's talk about these functions here, okay? Let's talk about these functions here. So the first thing that I want to talk about, so I just sort of gave you the answers with the functions, but let's talk about those, okay? So let's be clear, line, line, parabola. So this and this, these are lines, okay? Now, what I did is for this function and this function, I just sort of assumed that my origin was right over here. I thought that was pretty easy. So if I look at, let's say, this first one, okay, what do I know about that line? Okay, what do I know about it? I know that the slope is positive 29. And how do I know that the slope is positive 29? Because that's what the shear is right there, okay? Now, what about this point right here? That point is 0, minus 464, okay? So think about this. This is like y equals mx plus b, okay? So what's the slope? 29. What's the y-intercept? Boom. That's it, right? So that first moment function is 29x minus 464. That's it, okay? And I'm just using this as the origin, okay? Now what about the second one, okay? So let's look at number 2. Okay, what do I know about the slope? Okay, the slope is 4. And I also need a point, okay? What is my point? I can use this one or this one. It doesn't matter. If I'm using this as my origin, like if this is my origin, then this is x equals 16, y equals 0. Or I could say x equals 24, y equals 32. It doesn't really matter, okay? But from this, I can say four equals x minus 16, so y equals 4x minus 64, which is exactly what I got right here, okay? So no need for a section cut, it's a line, okay? With me so far? Now, so you were asking though, like your initial question is like you were sort of confused when to use a coordinate system, when to set it up, okay? So let me give you sort of a direct answer on that. This is a line, this is a line, okay? So because they're lines, what I'm doing is I'm just using a simple coordinate system over here on the left, and I can determine the equation of a line without having to do any, section cutting or equilibrium or anything like that. But this is a parabola, okay? So I don't think I'm going to be able to get around doing an equilibrium issue, or I don't think I'm going to be able to get around that in order to get this equation. So I think I am going to have to cut a section. So if I look up at the original structure and I ask myself, okay, if I'm going to be cutting a section through this region, which is the easier way to look, left or right, okay? I think it's a whole lot easier to cut a section and look to the right. There's less to deal with. So if I'm cutting a section looking to the right, what I want to do is cut a section and look towards the origin. So that's why I put a coordinate system over here looking that way. So if you do that, what do you get? All right, so, if I cut a section here, look to the right, what do I got? I've got $12 kips. I've got my distributed load looking to the right, so shear and moment, right? This dimension here is x2, because I'm cutting a section looking to the right. There's that distance. This load, 2 kips per foot, so I idealize that. 2x, x over 2, and so cutting a section at the cut and summing moments at the cut, I have m going like that. I have 12 x2 going like that. I have 2x, x over 2 going like that. M plus x squared equals 12x, or I guess x of 2. Like that, okay? So the reason that I put that second coordinate system over there, so the reason I did it is because I made that decision after drawing this. I drew the shear diagram and I drew the moment diagram and I went, okay, this is going to be easier looking that way. Does that make sense?
Yeah.
Okay. There is actually another way that you can get the equation of this parabola without cutting a section, but it's harder. It's more algebra. I can show you if you want. It actually involves just 3 equations, 3 unknowns, but you don't want me to show you?
So unless you want to, but if you think it'll be useful knowledge.
I don't think it'll be useful for the exam.
Okay, well then, that's okay.
Maybe I'll post a little video on how to do it.
Come on.
I'll give you, what's that?
Get to use them.
I don't care. But I'll just, here's what I'll do. All right, see how I'm using geometry to get this equation? So what's the equation of a parabola? The equation of a parabola is ax squared plus bx plus c. So there's like 3 constants that you need to solve for, right? Okay, well, this point is 0, 0. This point is 6, 36, if I'm going that way, and that point's 8, 32. So if you plug each of these points in, you get 3 equations, 3 unknowns, you can solve for A, B, and C. And, I mean, that's a way of doing it. I think it's more complicated than what I just did, though, so that's it. But that's a way. Okay. All right. I want to continue, though, on this problem to have a more, a longer discussion about it, okay? Because there's something that I think is really, really important, okay? So, let me draw it this way, okay? So let's draw this beam 2 times. Okay? So that's the hinge, right? And then let's do it again. Okay, so what does the real structure look like? The real structure looks like this, and then like that. Okay? And then this is (16-foot, 8-foot, 8-foot). All right, everybody okay with that? Okay, so the one point I really want to make about this is, if you look at the 3 moment functions that I generated, would it be fair to say that this region right here was in terms of x1, okay? And then this region right here was in terms of x2. I mean, is that fair? I mean, like, so when I wrote my equations, this was my x1 region, this was my x2 region, okay? That's the real structure, okay? For the virtual structure, okay, so if I am putting a 1.0 virtual load right there, you have to have apples to apples. So what I'm saying is, for this structure, this region needs to be of x1 and in terms of x2. You have to use the same thing, okay? It might be easier for this structure to write the whole thing in terms of x1. It might be, but you can't mix up your coordinate systems when you're integrating like this function with this function if they're written in terms of different variables. Does that make sense? Okay. So that's why if you scroll down here for the virtual structure, I'm using the same coordinate system. Okay? Now what ends up happening for this virtual structure, okay, is you get 1 down, this ends up being 1, and this ends up being 16. Before I start going down the rabbit hole, should I have a discussion as to why this reaction is 0? Feel like we're shaking heads yes? So part of the reason with this solution is I actually didn't provide a lot of details because I want you to work through this stuff together. All right, so ignore all the moment functions, ignore all that. Here's my structure. Let's get reactions for this structure right now. Okay? How many unknown reactions do I have here?
1.
1. Let's draw it up. Let's call it dy. How many reactions do I have here?
3.
Typically 3. So I'm going to have ay, ax, we'll call it am, what have you. Does that make sense? So, let's start off. Sum forces in the x direction. Ax is 0. Don't have to worry about that. Okay? Now, I want to be clear about something because I think this is a misconception that happens a lot on homework and on exams on Monday. I'm going to scroll down to this structure. Okay? For this structure, okay, this has a moment on it. Okay? So I think what a lot of students probably did is said, well, that's 0 and that's 0 because it's a moment. No. I am not saying that this is 0 and that is 0. I am saying that the sum of them is 0. That is the only thing that you can claim with this sum of forces in the y direction. Does that make sense? So here's what I'm saying. If we sum forces in the y direction for this structure, right now, what I propose is that ay plus dy is 1. But I don't know which is which, okay? I don't know which is which, okay? Now, what you could do is you could say, he's going to have to wait, all right? If you wanted to sum moments, if you wanted to do that, we don't have to consider ax, we don't have to consider ay. So if we wanted to do this, we could have am, we could have 1 times 16, and we could have dy times 32. So 16 equals am plus dy times 32. So am is 16 minus dy, or 16 minus 32 dy. With me so far? So, I know what ax is, I have an answer for that, but I don't know what ay is, and I don't know what am is. But would you agree that if I knew what dy was, I could get an answer? Samurai sword or lightsaber. So we're going to samurai sword or lightsaber through this. And then we get into this, like, philosophical discussion, okay? So if I cut a section, look to the right. I'm looking to the right because I'm interested in dy. All right, so let's cut a section. So we know we have that. But wait a minute, do I have a moment? No, I don't have a moment because I cut a section through a hinge. So we don't have to worry about that. Okay, I've got this reaction here. I have a moment arm of 16 feet. Is this complete? Like, did I miss anything in this free body diagram? Some of you are shaking your head yes, some of you are shaking your head no, because you're asking, where is this load? In other words, do I include the load or not? Okay? My answer is, who cares? Okay? And here's why. Why did I cut the section through the hinge? Tell me why. Why cut the section through the hinge?
So the internal forces would be 0.
Not your internal forces, your internal moments. You're cutting sections through the hinge because the sum of the moments is 0. Does that make sense? Okay, so I'm cutting sections through the hinge is 0. Does the shear generate moment? No, because it's going through the hinge. Like, technically what's going on, like, I draw it off to the side, but really it's like this. Does the 1 generate moment at the hinge? Because it doesn't have a moment on it. Doesn't matter if you draw it there or not, the distance is 0. The only thing we have is a moment going like this of dy times 16. So that's 0. 0 equals dy times 16. dy is 0. That's why dy is 0. There's no moment on this side of the hinge. There's nothing it needs to do. Okay? So if I go back to the original, to the problem, let me go back to the other page. Let me go back to the original page. All right? So if dy is 0, therefore ax is 0, dy is 0, ay is what? Well, if dy is 0, ay plus dy is 1, ay is 1, am, or the moment reaction, is 16. So that's how I got the reactions, okay? So now let's look at the shear diagram. What happens with the shear diagram? What do? I go up, over, down, right? You know that whole philosophical debate that we've had right here about whether or not to include the 1 or not? Do you know why we're having that philosophical debate? Because we cut the section right there, okay? The shear there is either 1 or 0. You think about it like this. Let's look at V. If I put the 1 there, V is 1. If I don't put the load there, V is 0. So the question is, which shear value is true at the hinge, 1 or 0? And my answer is both, because the shear jumps right there. It goes from 1 to 0. There's a continuous jump. Does that make sense? That's why we're going down. Okay? With me so far? Okay. So this is the shear diagram. This is the moment diagram. So here's what's going on. Okay? I'm gonna draw this a little bit lower. Okay. Here's what's going on. Here's my real structure. Everybody see the real structure? Okay. So we had how many moment functions? We had 3, right? This one was that. I mean, is everybody okay with that? I mean, those were the moment functions. If I look at the virtual structure in the same light, what did we get? A line function right there, but what do we get here and here? 0. Okay, and as for that linear function, do I need to cut a section? Well, no, right? Because what do we know about that little m1? We know that the slope is +1, and it goes through 0, minus 16. Does everybody see that? Everybody see that right here? So therefore, okay, can I erase all this over here? Can I erase all this? Okay. So how do I determine, what's the goal? I'm trying to get the vertical deflection at B, right? So what is my general formula? It is, that's my general formula. okay? But, I mean, look, here's the problem, right? Do I need to integrate this region right there? Do I need to do this? Because I'm multiplying by 0, right? Do I need to do this region? It's 0. So really all I need to do is EI, in this case it's EI1. That's my problem right there. That's it. Because, I mean, that's exactly what happened here. So when you set it up in the integration, I mean, you can do this integral, do this integral, do this integral, but they're going to go to 0. So all you've got is this problem, okay? I went ahead and just gave you the answer to this integral, right? Because, I mean, you can do that one pretty easily. It ends up being something like 118, what is it, 784 over 3? So this is a big old fraction. We have 1728 on the top. I think I did 118784 on the top, a 3 on the bottom. E for this problem was 29,000, and the I was 4,500. When you chug all that out, you end up getting something like 0.524. Does that make sense? Let's go back to your question. Did I answer your question? Because you asked the question about like what coordinates system.
Oh, yeah.
Okay.
For sure. Thank you.
But I also want to know about this problem. Is everybody able to get those vertical reactions?
Yeah, so for your virtual structure, did you like do your like cuts on the solution?
I didn't put them here, but I did them in order to get the answer.
You did, okay.
You
But
have
they're
to,
not
yes.
on there.
They're not on there, yeah. So like what's happening for the virtual structure is, can I erase this?
Yeah.
Okay, so what's happening for the virtual structure is, so keep in mind the only load on this structure is that moment, okay? So if I cut a section at the hinge and look to the right, here's my structure, here's the reaction, I have my moment of 1 right there, here's where I'm cutting the section, there's my shear, okay? I propose that there's a reaction right here. Now, I assumed it's acting downward, but let me show you why I assumed it's acting downward. All right, this distance here is x2. It's x2 because I'm in this region of the beam, and I use x2 here. I need to be consistent. So if I sum moments, I have a 1 going like that. I have to have something going the other way. Do you see what I mean? The 1 is rotating like this. Something has to rotate it like that. So let's assume dy is going like that. So dy times, I'm sorry, I said x2, but I cut the section at the hinge. This is 16 feet. This is 16. So dy times 16 is 1. Dy is 1 over 16. See, again, like, this structure, like, here's, okay. The big logical fallacy with a problem like this is if this is your problem and, you know, you have a moment like this, like this is all I'm giving you. That's it. That's all I'm giving you. You cannot logically claim, well, there's a vertical reaction here and a vertical reaction here, so they're both zero. That's not true, okay? I am not saying that they're both zero. I'm saying that their sum is zero, okay? Because that's not what equilibrium says. Equilibrium says that the sum of the forces is zero. It doesn't say if you have two reactions, they're both zero. That's a logical fallacy, okay? Does that make sense? So it was the same story over here, three equations. Now, with this one, unfortunately, you had to carry out all three integrals because you had, equation, 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 and you have moments across the whole structure, so it's a little bit more to integrate. But, I mean, it's ultimately pretty plug and chug. So, the only thing is you can't, so when you set this up, so like, normally what we've been doing is factoring out 1 over EI. You can factor out 1 over E, but you can't factor out 1 over I. You got to leave the I's in because you have different moments of inertia across the beam. So you got to leave those in there. So 1 over I times this integral, 1 over I times this integral, 1 over I times this integral. So I put the E out here, but different I's. Chug it out and you get like 0.178. Does that make sense? Yes.
I have a question about knowing how many moment functions you need, because I had 3 for the real one and then 2 for the virtual.
So that are you talking about which virtual?
That one.
So there are 2, right? But I mean there's 0.
Yeah. So you still include another one?
Well, so I mean here, okay, that's a good question, right? So I mean you're right that technically this is 0, but I think what I was, so yeah, you're not wrong there, okay, there's 0. But I think just the point I was trying to make is, okay, this is 3 integrals, right? So I'm just trying to think, do I need to use this function? Yes. Do I need to use this function? No. Do I need to use this one? No. Because they're both going to be multiplied by 0. You're right that this is basically just a single moment function. I think I wrote it with 2 different equations, but they're both the same. So, yes. So here's something I would say, okay, let's talk about that. Let's talk about the virtual structure, okay? So technically with this problem, okay, it's really only one function. This is actually only one line. So I actually proposed this, and this are the same equation, okay? Here's the difference, okay? Why is it different here and here? What's the difference between these 2 equations? The difference between these 2 equations is that the signs are flipped. This is x over 16 minus 1. This is negative x over 16 plus 1. This is basically that times negative 1 is that. So it's really the same equation. But why is it different? Why is it multiplied by negative? Why did I take this equation, multiply it by negative 1 to get that? Simple answer. That's why. The coordinate system is flipped. So it's the same function, just written differently. Okay? So I propose the moment expression from here to here, and the moment expression from here to here are the exact same. And it's really the same one here, just whoop, just flipped. So I'm basically changing the sign. Does that make sense? Was that one tough to wrap your head around? This was a difficult problem, I know. Who's next? You got a question?
I do. Mine is kind of similar to other Ava's because I, on the frame one as well, I felt like for the real structure I needed to cut 4, and then for the virtual one I felt like I only needed to cut 2, but I didn't know if you had to cut the same amount.
So let's talk about that. I have a sort of an older solution on that. We're running out of time, but I'll pull that one up here. So I have an older solution for that one. So for my solution, I'm going to present this a little differently when I post it to Blackboard. But so for the virtual structure, I did the for this problem I did the virtual one first. Okay. So this let me zoom in right here. Okay. This is the virtual structure, right here, okay? So, here's the structure. We're trying to find the horizontal displacement at E, right? Is that right? That's what we're trying to do. So I put a horizontal load here. So if I got one this way, here's a hinge, one that way. And so, again, they're not both equal to 0, their sum is equal to 0. So if you sum moments here, you got 1 times 16, it's got to be 1 times 16. So this is 1 up, that's 1 down. Okay? Everybody with me on that? Now, the thing about this problem is that there's 3 members. There's this beam, this column. What is going on this beam is absolutely nothing for the virtual structure. So little m for this beam is 0. Big M for this beam is who cares, okay? That is the big point I want to make for right here, okay? So let's talk about this and this. So for this beam, if I say x going like that, this is going to be 1 times x. Okay, so this little moment function is x. This little moment function for this one is x, because it's just 1 times x. Okay, so if you look at your virtual structure, I've got basically x's. Like little m is equal to x for both members. Now for the real structure, okay, here's what I'm saying. So here's the real structure. Compute reactions. Again, if you didn't match my reactions, that's something I want you to practice. In the real structure, is there a moment function for this member? Yes. I don't care what it is because it doesn't matter. Okay? All right? This member has 1 moment function. So when I integrate this member, I'm going to have an integral from here to here. Okay? When I integrate this member, I'm going to have 2 functions. I'm going to go from here to here, here to here, okay? So when I set up the final problem, like let me go to the very, very final problem, okay? What I'm saying is I'm going to integrate the column from A to B and from B to D. And so the way I set it up in the solution, I said, here's my origin, here's my coordinate system going up, here's my origin and my coordinate system going that way. Integrate this from 0 to 8, integrate that from 0 to 16, integrate that from 0 to 16. I'm not using member CE because there's nothing going on there on the virtual structure. So here's my big M function, here's my little m, here's my integral, sum them up, 1728 over EI, plug and chug, and I get a horizontal displacement of 2.27 inches.
That makes sense, yeah. I was like, I didn't know if you had to cut the same amount, because I think I did that first, and then I went back and I was like, let me cut another section on the virtual, because but
yeah.
That makes sense. So you just use the same function since it's the same, like, over
For the
same
virtual
amount.
one, yes.
Yeah.
Yes, because if you look in the table, you'll, if you look here, notice how my virtual function didn't change. My real one did.
Mhm. Gotcha, thank you.
No problem. Any other couple quick questions?
Can you give us the answers?
I cannot. That was a good try.
That was a quick question.
It was quick. It was a quick answer. No.
So,
No further questions?
Hold on, whoa.
so, like, for your deflections or for your rotations, the unit ones, does it matter what direction you put it as long as you correct for the sign?
So, okay, let me answer that question globally, because that's a really good question. So the question was, does it matter what direction that you put it in? Here's going to be my answer, okay? Let's go to the virtual structure. I drew this to the right. If I were to draw this to the left, what it would do is it would flip that, flip this, flip that, they'd all be flipped, okay? Now, the coordinate systems have to stay the same. This has to stay going like that, this one has to stay going like that, this one has to stay going like that. Make sense? What would happen, let's say you assumed incorrectly. Here's what would happen. Instead of a positive x, you would get negative x here and here. What that would do is it would make the resulting integrals all negative. These integrals would all be negative. If these integrals are all negative, what it means is this sum is negative. So I got a positive 2.27 to the right, you would get negative 2.27 to the left. But a negative deflection to the left is a deflection to the right. So basically what that means is you assumed incorrectly, so it's going the other way. Same thing with reactions. So. Sound good? It's a half day at school with my daughter, for my daughter. I got to go pick her up. So I will see you. It's 11:50 anyway, so.
After my